thanks for now. So thanks for the introduction and many thanks for inviting me to give this lecture. And yes, you pronounced my name really good. My name is Uwe Rascher from the Forschungszentrum Jülich, and as also Onno introduced, I'm working with plants for several decades, and in the past years I tried to combine the methods, the phenotyping technologies with remote sensing. And in this respect, I try to share my screen, so you should see my title slide now. And what I would like to do with you, as already announced by Onno, I really would like to go in a little bit more of a lecture type format. And I really hope that I did manage to find the right level of abstraction or complexity, because I have to admit, I don't know the audience here yet, but I think we will have the chance to maybe even meet in person in the future. But what I want to do today with you, and I hope that you can also see my cursor on the screen, is that I want to take you a little bit in the spectral domain. So I want to tell you or give you a concept, at least my thinking, what is the nature of light, and want to guide you through how we can explore this spectral space for plant phenotyping. And this then lead us to the more a little bit technical part, which sensors are available, which cameras we can use for plant phenotyping. I will mainly stay on the close range for this lecture, so but you will see that during this talk there was from time to time there will be some excursions to the field, to the larger scale, and maybe even to the airborne and satellite scale, because when we want to understand how plants work, how happy or healthy plants are, and if you want to use phenotyping to produce a new breeding line for the future, ultimately we have to go in the field. So everything which I present today is pretty much field ready, and we can use the concepts which I will show you today. So on the one hand for the laboratory, but also for the field. And just to set the scene, plant phenotyping, I think you're all totally aware that with this phenotyping, we try to quantify physiological and structural traits of plants, and that with the introduction of the last lecture, I think you already were exposed and you know this high-tech, new, very fancy greenhouse facility for plant phenotyping, which Rick van der Sette presented in the last lecture. And I don't want to repeat this because there are many talks and also online resources available which introduce you nowadays to plant phenotyping. Sorry, the movie is not starting, but similar like this movie, there are also several other movies on the web, and I give you here just as a starting point 2 potential resources where you can have online resources, talks from summer schools and conferences on the current state of the art of plant phenotype. And the topic of my lecture today is, as introduced, I would like to dive a little bit into light. What is light as one of the tools which we use pretty often to measure plant structure and function. And in principle, if as a non-physicist, and I assume we are all not quantum physicists here in the lecture, so for a non-physicist, we can assume that light is just a stream or flux of photons which travel with light speed. And the properties of this flux of photons can be best described by a wave function. And this wave function, if very in the easiest way, if I want to describe a wave function or the characteristics of a wave function, I can either describe the wavelength of this wave function, so the distance between the two maxima or two minima, or alternatively, I describe the frequency, means how often does this wave function oscillate or reach a maximum within 1 second. And these two parameters are interconvertible. And in principle, you just have to keep in mind, if you measure one of the two, like wavelength or frequency, you have already a very good description of the energy of this electromagnetic radiation, of this flux of photons of light. And pretty intuitively, the higher the frequency, so the more fluctuations you have, the higher is also the energy which is carried by this electromagnetic radiation. And this leads me to some graphs or schemes which you may know that this whole spectrum of electromagnetic radiation can be sorted from electromagnetic radiation of less energy to more energy, and you can either describe this energy by the frequency or the wavelength, and that the in a different, just a different representation, but the same content, that the visible light, which we normally speak about, if we speak about light, is just a very small, tiny window in the middle of this whole possibility of electromagnetic radiation, which we can use for measurement purposes, which is also emitted by the sun or the greenhouse lights in our measurement facility. So if we speak about visible light or the visible spectrum of electromagnetic radiation, it became common that we use a wavelength measured in nanometer as the appropriate unit. It just gives nice numbers. So the visible light for the human eye is between 400 or 780 nanometers and approximately 700 nanometers. Just a convention to describe the color or the energy of the photons which are visible for us. However, today I will move with you also out of this visible spectrum. I will move with you in the other spectral domains of electromagnetic radiation, because even though we cannot measure or we cannot see them with the bare human eye, we still can use it for our measurements. So, and if you think about electromagnetic radiation, one thing which I always try to tell my students is be aware that the flow of photons which you use for your measurements is not homogeneous and may, at the first instance, you have to understand first what is really the spectral intensity of your incoming light. And I make this example now with the first example from the real field. The sun is our main source for light, for electromagnetic radiation, and the photons which are emitted from the sun, which travel with 300,000 kilometers per second towards our Earth, the first thing which they hit is our Earth atmosphere. And they penetrate through this Earth atmosphere. And on this path through the Earth atmospheres, the photons already interact with the trace gases and the gases of our Earth atmosphere. And during this path, they are refracted, scattered, and partly also absorbed by the components of our Earth atmosphere. And if I look on the intensity of the photons, which I measure on the ground with a sensor, with a spectrometer, and if I look on the intensity I see, and this is this white curve, the lowest white curve, this is the intensity of the incoming photons on the Earth atmosphere. And you can already see from this representation, here we have the visible light, there it's reasonably smooth, but if you go out to other spectral domains, the spectral signature of the incoming photons is a pretty complex one because of the absorption of the photons through our Earth atmosphere by water, by oxygen, and other components in our Earth atmosphere. So this is the first thing, that incoming light, or the light which we use for our measurements, may have a pretty complex spectral signature. And a similar complex signature you will also find if you hold a spectrometer under your measurement lamps or your growth lamps in the greenhouse. And you may know this emission characteristics of your growth lamps can be pretty complex, and depending which kind of lamps you have for growth, which kind of lamps you have for measurements, this incoming flux of photons is fundamentally different, even though they may all appear pretty wide to our human eyes. And then we come to the next point. So we have a flux of photons from our light source or from the sun, and then these photons interact with the object which we want to measure, with a tree, with a leaf, with a surface which we want to measure. And this interaction is normally, there we'll talk a little bit about, so either the photons are reflected, they are transmitted, or they are absorbed. And before we go in these three main components, reflection, transmission, or absorbance, always keep in mind that there's another process happening behind that. All these things may happen in different directionality. So for example, on reflection, if you think about a photon which hits a surface, it may be reflected in all different directions in space, which is then a so-called Lambertian reflection, or it may have more a preliminary or primary direction in which the photons are reflected. And these things often are neglected, but try to keep this in mind, because this has a pretty big impact on where you actually place your sensor if you want to measure the reflected light from a surface. But now back to the absorption. In essence, the most important part we are interested in is the absorbance of the photons with the material in our plants. And I now zoom into the molecules of the plants. And here you see the main molecules which you may be interested to measure: chlorophylls, carotenoids, anthocyanins, and so on. And if you look on this chemical structure of these pigments, we see a pretty common scheme in most of these pigments, which enable these pigments to interact with photons, which bypass with this nice speed of 300,000 kilometers per second. And these chemical schemes in these pigments are able to now interact with the photons and actually take over the energy of the photons. The photon, by this process, totally disappears, and the energy is transferred to the pigment. The pigment is then shifted to a higher energy-rich state, often called S1, S2, sometimes also S3, S4 for singlet state. So the energy of the photons is fully transferred to the pigment of the plant. And this is something which the plant sometimes wants because, for example, in the case of photosynthesis, this energy is then used to drive the photosynthetic machinery. I will come back a little bit to photosynthesis at the end of my talk. But now let's talk again about this absorption, the light absorption. This absorption of the photons, as a matter of fact, is really specific and is closely related to the energy or the wavelength a photon has. And this is the absorption spectrum of three really well-known pigments: chlorophyll A, chlorophyll B, and a bulk of carotenoids. And you can see from this graph that, for example, pigments which have a wavelength of 550, 580 nanometers almost never interact with this pigment. The energy cannot be transferred, and therefore there's a really low absorbance. Other wavelength regions, like for chlorophyll, around 440 nanometers, the pigments interact really well with the photons of this specific wavelength, and therefore they are absorbed to a high probability. And this specific absorption feature of every pigment, that's what we try to use in spectroscopy. So we really try to understand what is really the specific wavelength-specific interaction of every molecule with the photons, to then use this information of absorbance to understand what pigments, what constituents are available in a plant. And having said this, a first step which never should be forgotten is that we have this weird spectral non-stable flow of photons, which is the incoming measurement light in most of the cases. Therefore, we have to normalize to get rid of this non-stable in spectral space, non-stable incoming flux of energy. And what people normally do is that they do a very simple normalization. So we divide the amount of reflected photons by the amount of incoming photons for every specific wavelength. And by this, we then have the percentage of the reflectance per specific wavelength. The same thing can also be done for transmittance. So also the transmittance, if you place the sensor underneath the leaf, you can also measure the transmitted photons, and you normalize the transmitted photons by the amount of incoming photons, again, at the specific wavelength. And if you have this, then you have the main components which you can measure. You can measure the reflectance, you measure the transmittance. Both describe or the residual after this are the photons which at the end are absorbed. The three processes always add up to one. So a photon cannot be lost. It's either absorbed, then it's lost, but it's absorbed. It can be transmitted or reflected. And the spectral characteristics of these three parameters is really specific for a pigment. And what you see here is the full measured reflectance, absorbance, and transmittance spectrum of a leaf, a natural leaf measured in an integrating sphere. And you can see that there's, for example, the visible light and high absorbance, then almost no absorbance in the near infrared. And then there's a more absorbance again if you move far beyond the visible range, beyond 1,500 nanometers. And this is a spectrum of a full leaf. And if you want to be there really precise, and some people do this, if you really want to unravel this, you have to be aware that the path of the photons through a leaf and within a leaf is pretty complex. So it's not only the transmission, absorption, and reflection process, but there are several interactions of the photons with the surfaces of the single cells, with the pigments within the cells, and so on. And the path of the photon can be pretty complex before it actually reaches your sensor, which being either placed on top or below the leaf. So this is a whole part of plant phenotyping. If you have fun and if you want to go in there, people have developed models to really understand these optical properties within single leaves. There are models available which you could use to really physically model and understand the properties within a single leaf. But let's be a little bit more pragmatic now for our more pragmatic plant phenotyping. Let's look on, for example, the overall changes which happen if I, for example, change the chlorophyll content in a leaf or if I change the water content. Down here, this is now a modeling study taken from one of the models, which I said it's a physically based model, and we just only change the chlorophyll content and the water content. And if you look on the reflectance, which are related to these changes of the two constituents, you can see that the two constituents leave a very specific signature. Water interacts in the near infrared and shortwave infrared region, therefore changes the reflectance there, while chlorophyll has the two absorption features which I showed before, the visible range. So the interaction of the single components and the translation to the reflectance signature is really specific for the leaves. And if we now measure over a full leaf, we try to unravel these changes in the reflectance. I'm talking about reflectance, but similar things can also be done for absorbance, but I'm now talking about reflectance. And we can observe the changes of reflectance and try to relate this to changes which happen inside the leaf. And this is a very simple experiment which colleagues at the University of Zurich did. And they just took a leaf, detached it from the plant, and let it dry for 8 hours. And down here, this is time running. And at the beginning, you see this nice reflectance curve, and I will come back to this reflectance curve. And in the first hours, you see mainly a change in the shortwave infrared, which is related to a process which intuitively you will hopefully agree that happens, namely that leaf loses quite a lot of water. And the first process which we see at the very beginning are changes, pretty rapid changes in the main water absorption bands in the shortwave infrared, which change at the beginning. Then after 3 and 4 hours, we see another change here in the visible light. And after 3 and 4 hours, also the pigments, the photosynthetic pigments of the plants, the chlorophylls, the carotenoids are degraded. So the leaf turns yellowish. And then we also, with this time delay, after 3 hours, nothing at the beginning, but after 3 or 4 hours, also in the visible range, we see this change. And this is a little bit this illustration of the spectroscopic measurements which we want to do. So these are the measurements which we have, and we try to use our knowledge of the absorption characteristics of the components, and we try to relate this then to concentrations or to information about the constituents within the plant leaves or the whole plant. And in this context, to describe these changes, which I showed before, again here in the upper graph, you see the same reflectance curve of a healthy leaf, which I showed you before. So again, wavelength, it's a little bit hard to read, visible light down here up to 2,500 nanometers. And this is the relative reflectance which we see. And we know in this range, the chlorophylls, the carotenoids mainly absorb here water, but also cellulose, lignin, and other constituents have their main absorption feature. And the first thing which people did is that they used some specific characteristics in the reflectance curves, which are specific for plant constituents or plant components, and developed so-called vegetation indices. And the first vegetation index was the so-called simple ratio. And this was just the ratio between the reflectance in the near infrared and the reflectance in the red. Knowing chlorophyll absorbs a lot here, and does not absorb at all here in the near infrared. So you take two closely related wavelength regions, you take the ratio out of this, and you calculate this simple ratio where you say, well, the higher it is, the higher the difference it is, the more chlorophyll is available. Developed in the 17th, still used until today, but then people said, this value range between 0 and 7 is kind of hard to use as a quantitative measurement. So they used a normalized version of this index, a normalized difference vegetation index, where you subtract the near infrared reflectance by the red reflectance, and you divide it by the sum of both. This has the big advantage that you get a value between 0 and 1, and this 0.1 value really can be related to the chlorophyll content, or if you use it on top of the canopy, the total amount of the chlorophyll, which is often then related to the LEI or the leaf area index multiplied by the total amount of chlorophyll. And after the NDVI was, I think, in the 80s, the main vegetation index where people or NASA also started to shoot the first satellite into space. So Landsat was such a success story because it had exactly these two bands which were needed, a near infrared band and a red band to measure vegetation. So this was the first satellite which was really built for vegetation measurements to provide NDVI. And then after this NDVI formulation, if you open the literature, you can nowadays find a lot of, I call them greenness indices, which have fancy names. Let it be the NDVI red edge, the EVI for advanced vegetation index, the TCARI, the transformed chlorophyll absorption reflectance index, and so on and so forth. I think you can pretty much 40, 50 vegetation indices, which all measure the greenness and the amount of chlorophyll in vegetation, are available in the meantime. And even though the formula gets a little bit more complex, mainly they exploit the transition of the red absorbance to the near infrared non-absorbance of vegetation. And this really separates green vegetation very clearly from all other components which we have on Earth. This is a collection of a few random reflection spectra. And even if you look at the orange one, sorry, Kunstrasen is artificial grass. It's an artificial surface which looks green to the human eye. But if you look exactly on this reflectance curve, it does not have this sharp transition between the red and the near infrared. So these reflectance indices or these vegetation indices exploit these dynamic changes of chlorophyll, and there are a lot of variations of the NDVI, but then not only on the NDVI, but also on other indices which use other absorption features from other components in the plant. So you can, for example, think about if you want to measure lignin, why don't we use this absorption of the lignin at 1,400 nanometers? And there a lot of vegetation indices are then published in the decades after this to measure, for example, nitrogen, lignin, cellulose, carotenoids, anthocyanin, and so on and so forth. Authors run out of names, so they even started to number them as anthocyanin reflectance index 1, 2, and 3, I think is also available. And the background behind that is that they all try to resolve this characteristic absorption features by using 2, 3, 4 specific wavelengths for this component. There's, however, a danger behind this. And the danger is that while chlorophyll is really specifically absorbing here in the near infrared, lignin, for example, starch, is absorbing in the range where also water absorbs a lot. So there's a lot of overlap and non-specificity in all these indices, which I have mentioned here, because the absorption features, especially in the shortwave infrared, are not as sharp as the chlorophyll one, and they are overlaid and not specific. So they are overlaid between cellulose, lignin, water, and starch. That I would always say, be really careful in using these vegetation indices. Look on the waveband and really think about what they are really measuring and how specific they are at the end. And this becomes especially clear if you move from the lignin and cellulose to, for example, water. So people have developed also water absorption indices to measure the amount of water in a leaf. And this is the same problem as we had before, that this is not only water, but also other cell constituents. And if you think about water absorption, we also have the problem that the incoming light always is not stable at all, that we have a lot of atmospheric influences of the incoming photons because of the absorption of water, of photons by water vapor in our atmosphere. And you know, water vapor changes quickly in our atmosphere. So also these measurements, especially in the field, are always unstable just because of clouds moving. And with this having said, and hopefully having given you an introduction and the knowledge behind what's behind this vegetation indices and how we can use this, a short excursion to some indices which are called functional indices. And there are also vegetation indices on the market, and I just take the PRI, the photochemical reflectance index, as one example, which claim to measure functional, means physiological properties of plants by exploiting subtle changes in the case of PRI between 531 and 570 nanometers, which are associated to the non-photochemical quenching of photosynthesis. And in principle, there's nothing wrong in this. The information is contained there, but same problem as before. There's also a big influence of other pigments, like, for example, chlorophyll, which also leave a signature in the PRI. And if I want to be blunt, I would say in a lot of literatures which you see where the PRI is used as an indicator for non-photochemical quenching, people actually observe the degradation of chlorophyll and not the dynamic adaptation of the NPQ mechanism by itself. Of course, people realize this. So in the meantime, there are also corrections methods around again, but take home message for us to now PRI or this functional indices can, from my perspective, not easily be quantified by reflectance measurements. What I mean with not easily, the functional or physiological changes in leaves which affect the leaf absorbance are pretty minor and are very minor extent. Even though they are related in our signature, the changes are often subtle and often really hard to distinguish from any other structural changes, total pigment bulk changes, which may overlay in the reflectance signature the structural change, the underlying structural changes. And therefore, this is latest the point where I would say we cannot work with simple indices anymore. There we really have to go in advanced methods to retrieve this signal. I'm not going in my lecture in this topic because this would be another 45 minutes if you want to touch into nonlinear regression, spectral unmixing, or machine learning approaches, which are currently being developed. I'm not sure if you plan a course or a lecture on this topic, might be of interest in this course, but also there are a lot of YouTube lectures in the meantime available if you want to get a good start. My colleague Uwe Rascher has an own YouTube channel, especially on this topic of machine learning and advanced retrieval mechanisms for plant observation, for optical plant observations. Another thing which is promising is if you measure fluorescence, and fluorescence then at the end is not a reflectance measurements anymore. We measure something slightly different. If I have time at the end, I can give you a short introduction in fluorescence or how this is linked to the measurements or the topics which I have taught so far. But back to the reflectance measurements. A little bit technology, 10 minutes maybe of technology. So if we want to use the signal, we also have to think about how do we measure the spectrally resolved signal with our sensors. And the easiest way to measure the photons is normally that you integrate over a specific spectral window. And the most commonly used sensors are the so-called PAR sensors, photosynthetic active radiation sensors, and they are normally built in such a way that they measure and are sensitive exactly for the wavelength region between 400 and 700 nanometers, which is the wavelength region for photosynthetic active radiation. But with these, sensors, we only cover this visible range of spectrum. Visible range and photosynthetic active range is by chance pretty much the same. But we also sometimes use sensors which extend to other spectral windows, and there is a whole range of different sensors available which have a measurement window, which is normally very well described to measure, for example, the near infrared region, which is defined between 700 and 3000 nanometers, or also the long wavelength infrared beyond 3000 nanometers, or like seen here in the UAV range. And then you may have thought about, well, what's about thermal sensors? Yes, thermal sensors also measure electromagnetic radiation, but in the range of 8 to 14 micrometers, so 8,000 to 14,000 micrometers. So it's pretty far off my grid. And if you really want to measure the thermal radiation, which is then also an emitted radiation of an object of a specific temperature, this is not reflected, and this is not reflection anymore. It's really the thermal emission, which you can also detect with specific thermal sensors. That's different than the long or near infrared radiation, which is a reflected radiation, which is also sometimes referred to as heat radiation, but that's different than the real thermal radiation in the physical sense. Okay, sensors which measure just over one spectral window was the first start. Then the next sensors, which I think you all know, are the so-called RGB cameras or camera cameras. And RGB stands for red, green, and blue channel. And if you look on the sensitivity of such a camera, this is one example camera, then we have the 3 detectors in this camera which are sensitive for blue, green, and red photons. And what you already can see here, these are cameras which are built to reproduce pretty pictures for our human eye, but not necessarily pictures for precise measurements, because there's a lot of overlap and non-specificity in the sensitivity spectrum of these different channels. And for example, photons, in this case 580 nanometers, they are absorbed by the green, and also by the red detectors in the camera. But nevertheless, RGB cameras, they are cheap, they are high performance in the meantime, and this 3 color information can be used also for getting some information about the color or the absorbance quality or absorbance characteristics of a component. What we then use a lot for plant phenotyping or for plant research are the so-called near-infrared cameras. And these are cameras which are built to measure there where plants reflect a lot of photons, namely around 800 nanometers. I showed this before. So these near-infrared cameras are cameras to selectively see the high reflection of vegetation. So these were cameras which were also brought on the market, reasonably cheap, easy to use. And one then logical development of some camera manufacturer was to combine these 2 cameras, to combine an RGB camera with a near-infrared camera in one housing. And it's really so simple as it's here schematically shown. So you have the incoming light, the light beam is split, the visible spectrum is fed into the RGB camera, and the near-infrared spectrum goes to the near camera. And by this, you already have 4 channels for measuring by just one camera, by one 4 lens. And this is already a good system where you can, for example, separate the high reflectivity in the near infrared from the low reflectivity in the red. And parameters like NDVI can already be calculated in relative terms by such a camera. The next development then was that people wanted to use a little bit more sophisticated and better separating filters for their camera system. And they used filter wheels in a camera system which have a good separation of the different color channels, so broadband filters in front of one camera. This was pretty much the technology about 25 years ago. These moving filters had some technical problems. And then with the fact that cameras became cheaper and cheaper, it became feasible to actually use more cameras in parallel and to equip every camera with a specific bandpass filter. And this was one of the first cameras being put on the market with 6 channels. In the meantime, they became more and more miniaturized. And these kind of cameras, they are really only 10 centimeters big, with pretty good performing cameras in this aligned multi-camera setup. This is the measurement approach, which is now the cheapest and most widely used camera approach, for example, for field measurements with UAVs. These are these multispectral, operational multispectral cameras for UAV or field measurements. And with this, we can get already pretty far. So by combining 2 of the cameras, we already have 10 different channels. And in this graph, I showed you a comparison of the bands down here. These are the spectral bands which you can order off the shelf for a decent amount of money for this multispectral cameras. And these are the bands of the recent satellite which was put into space, Sentinel-2, which is the European Space Agency vegetation monitoring satellite. And if you look a little bit closer and with some idea, the bands of this high-tech satellite pretty much overlap with the bands which we have there in those cameras. So the development is pretty much in parallel. The satellite develops vegetation indices, and also with this camera, their bands are designed in such a way that we can measure the relevant vegetation indices for vegetation to be related to plant traits. However, the technology moves on, and people wanted to move further and to move towards hyperspectral measurements, so not only multispectral measurements, which I just talked here before, but really have a continuous spectrum of a measurement. And this is the definition of a hyperspectral measurement, that you really have hundreds of wavelengths which form a continuous spectrum, not discrete bands anymore. And the most of the detectors which are reasonably affordable are still point sensors, where you use a point sensor and then you measure the reflected photons with this point sensor. Think about where to place the sensor, as I said at the very beginning. But with this, you then get a reflectance, a relative reflectance signature of a surface, for example, a paprika or a leaf. And this is the technology which is also used currently on airborne remote sensing, and which is currently being developed for satellite remote sensing. While in the past we have measured multispectrally, now also the imaging spectrometer are becoming operational for airborne use and also for UAV use. And the first hyperspectral satellites are being built by the big space agencies to become operationally available to then also provide hyperspectral data from space. The technology behind there is then normally not anymore a camera system. And this has something to do with the way how you can measure this signal. You cannot work with filters anymore, but it's normally a slit and a push probe spectrometer, where the final scene is resolved by moving the sensor or the object forward, and then the object is scanned spatially in 1 dimension, and then finally a 3-dimensional data cube is produced. There are also the first hyperspectral sensors, hyperspectral instruments for indoor plant phenotyping facilities available. Especially conveyor belt systems are useful because the plant already moves and you have this one forward movement already available. But also for the field, we are detecting or using these field spectrometers as a push probe sensor for measuring in high precision some plant canopies. So, and with this, again, some technology development, some manufacturers were able to reduce the technology again to have reasonably small sensors. This is one sensor distributed by Specim, which we had the chance to test in an early version, which is one of those push broom sensors. So to use the sensor, it's small, it looks handy, but nevertheless, you have to hold still for 15 seconds because this is the time it is needed to scan a full scene. And also other camera manufacturers have now tried to put this technology of several bands, multiple bands on the single chip, and also produce gradients on single chips, which allows a slightly faster measurements, and then being implemented again in snapshot cameras, which is kind of handy for phenotyping. And this is a new technology which is currently being exploited, and you may have seen this. These are the so-called, sometimes people call this the IMEC sensors, where not only 3 colors are on the chip, but in this case, 4x4 or also 5x5 colors up to the newest technology. Transits are implemented directly as filter layers on the chip. But with this, I would leave the technology. So this is the background technology which you have in all the sensors. And I think if I look on the time here, I could maybe use another 3 or 4 minutes to briefly introduce you to photosynthesis, because what I said before is namely that the 3 components, reflectance, absorbance, and transmittance, are the only fate of photons. This was almost true. But you have to keep in mind that from the light which is absorbed, so from the part of electrons which are absorbed and cause an energy, are stored as additional energy in the pigments, some of these electrons may be re-emitted again as the so-called photosynthesis, fluorescence light, or fluorescence photons. And this happens as an inverse process after light absorption, means photons disappear, converted into energy. The inverse process can also happen, so energy in the pigments can be converted back to a photon, and the energy can be re-emitted as a fluorescence light, and this is then the fluorescence, this definition of fluorescence, so the conversion of the excited state to the ground state by the emission of a new photon is called fluorescence. Fluorescence happens in the case of chlorophyll in the red range. And the nice thing is that this fluorescence signal is a direct indicator for the amount of energy in this excited state. So you can kind of schematically picture, if you think about photosynthesis, the plants want to absorb photons to use and to harvest the energy. And this energy is normally transported from the reaction center into the light reaction of photosynthesis. However, all the photons or the energy which cannot be used in photosynthesis, as some proportion is re-emitted as fluorescent signal. And if you find the plant in a situation where there's more light than which can be used in photosynthesis, the fluorescent signal changes and in the first instance increases. However, the plant is clever. They try to avoid an over-energization of their reaction center, which can cause harm. And therefore, there's always a third pathway, which we have to keep in mind, which is the so-called non-photochemical quenching, which also dissipates excessive energy and which is actively up and down regulated. But nevertheless, by measuring the intensity of this fluorescent signal, we have an insight into the energy available in the reaction center, which potentially can be used for photosynthesis. And this is the reason why people spend a lot of time in exploiting this fluorescent signal, especially recording the dynamic changes of the intensity of this fluorescent signal, because this is an indicator for the energy available for photosynthesis. All green plants fluoresce. If you look on this fluorescent signal with a sensor, with a bare eye, we see it as a red light. With a sensor, we realize it has 2 peaks, and these 2 peaks come from the 2 photosystems, which could differently contribute to the 2 peaks of the fluorescent signal. And we, as plant physiologists, we like to exploit the information content of this fluorescent signal. However, we always have the challenge that the fluorescence contribution to the total amount of light which we measure is really small. This is a modeling study which we did in our house. So the black line is just the reflected light, and the red light is the reflected light plus the fluorescent signal. So pretty much these little tiny changes or differences, this is the fluorescent signal only, which we try to use for measurements. And to solve this problem in the past years, we have always used active methods for fluorescence measurements. And you may know this, there's this PAM approach, but also the lift approach and others, which are all active methods. So an active, normally pulsed or oscillating measurement light is shot on the plant. And then with a dedicated measurement system, only the fluorescence light is detected. In the past year, I would say almost in the past 15, 20 years, high performance spectrometers are able to use some properties of our Earth atmosphere, namely the absorbance, the specific absorbance in our Earth atmosphere, to also measure the fluorescence light in some of those absorbance light. These are some tricks, and this would be another lecture from my side, but these are the newest development which is currently being exploited to have not only active fluorescence measurements, but also the way to passively measure fluorescence by just using the normal background light. I did not put a focus on this because these passive measurements of fluorescence are mainly field methods. We use some properties of the Earth atmosphere and of our solar sun. So all these methods cannot be used in the greenhouse. So these are all field methods. But for the field, they have the nice chance that they can be scaled. And when I said at the very beginning, even up to the space segment. So one of the recent developments in the science fleet of the European Space Agency is a satellite which is called PHENOWEX, which will be launched in 1.5 years from now, or maybe 2 years from now. And PHENOWEX is the abbreviation for Fluorescence Explorer. So a satellite which specifically measures the fluorescence emission of our Earth vegetation globally. But with this, I think I have moved far away from phenotyping, but I think plant phenotyping at the end is somehow linked also to plant production and understanding plants in this natural environment. And with the methods, by using the power of photons and energy, I think we can really scale at least the methods from the greenhouse to the field, but also to larger regions. So, and with this, yeah, 46 minutes, I think I should come to an end. Just 3 articles if you want to read more about the background which I was talking about. There's a recent review article from a colleague of mine, Michelle Watt, who's now back in Australia, about plant phenotyping for breeding. With Fabio Fiorani, I have written a review about almost 12 years ago, where some of the pictures from this lecture were taken. And then also, if you want to know more about measuring photosynthetic properties specifically, there's a nice review from Eric Murchie, published about 6 years ago. And with this, I thank you for your attention, and I'm here for your questions, comments, if there are. Thank you very much.
Thank you very much, Uwe. Stop the recording. And with that,